Okay, so let's talk about the experiment that you're going to do, the sodium tetraborate KSP. Now, I love this experiment because it's going to tie together a lot of the concepts and techniques that we've been talking about this quarter. Now, what you're going to do in this experiment, I'm going to give you an overall idea. You're going to figure out the delta G, the delta H, and the delta S for the solution of borax. The solution just means dissolving borax in water. The solution of borax in H2O. So far, so good. Okay. Now, how are we going to do this? The way we're going to do this, again, this is an overview, and then we're going to go over it in detail. We are going to do a titration. You love titration. We're going to do the titration, and when we get the titration result, what we can get out of it, we can figure out the equilibrium constant. Okay? And the equilibrium constant is KSP in this experiment, which I will talk about in a second. But the key is what you're going to figure out. You're going to figure out the equilibrium constant. Okay? So do the titration, figure out the equilibrium constant. Once we figure out the equilibrium constant, what we're going to take advantage of, we're going to take advantage of between the equilibrium constant and delta G. Because remember, equilibrium constant and delta G are related. Equilibrium constant, delta G are related. We're going to use that relationship to figure out delta G, and then from there to figure out delta H and S and all that. Okay. Now, I want to remind you how these two are related to each other. Remember, energy is a driving force for a reaction, right? So energy, which is delta G, is a driving force for a reaction. Now, in order for reaction to reach equilibrium, what do you need? You need energy. So driving force for reaction to reach equilibrium, there's energy associated with it. You need energy to reach equilibrium. So equilibrium constant and delta G are related. So far, so good? Okay. So what we're going to do, this experiment, you're going to have sodium borate. I'm not even going to bother to write the formula. Sodium borate. Sodium borate is going to be solid. And then what you're going to do, you're going to add it to water. There's going to be an equilibrium. And some of the sodium borate is going to break up into ions. And borate, just going to put -2. Okay, so here is the equilibrium that we're working with. We have sodium borate is our solid. There's going to be an equilibrium when you add borate to water, and then some of it is going to break up into ions. Now what I'm going to do, I want to write an equilibrium constant, right? Now remember, equilibrium constant, it was product over reactant. Nothing you haven't seen before. Equilibrium constant was product over reactant. What is my product here? My product is sodium. Let me write it with a different color. So my product is sodium plus. I have 2 of it. So to the power of 2. So concentration of sodium plus to the power of 2. And then concentration of borate. And I only have 1. Times concentration of borate to the power of 1. Okay? Over, so it's product over reactant. Over, what is my reactant? Sodium borate, which is a solid. Remember what we talked about. Because when you have a solid, the concentration does not change. So we do not include solid in an equilibrium constant equation. So equilibrium constant, we've done this before. Product over reactant, nothing new. My product is sodium to the power of 2. Borate, so just 1 to the power of 1. That's my product over reactant, except my reactant is a solid, so I'm not going to include it in my equilibrium constant equation. Okay, so this is my equilibrium constant. And specifically, what they call this equilibrium constant, they call it KSP. You know how we have Ka for acid, Kb for base. KSP, the SP is solubility product, because again, it has to do with we adding a solid and see how much of it would dissolve, how much it is going to be soluble. That's what we call it, KSP, solubility product. We're adding in a solid and we're looking at this solubility product, how much it will dissolve in water. So far, so good? Okay. Now, what we want to figure out, the goal is, what we want to figure out, we want to figure out how much of this borate will dissolve. Okay? So we want to figure out how much borate will dissolve. That's the goal. Now, how are we going to do that? So to figure this out, what we're going to do, we're going to make a saturated solution. Okay? We're going to make a saturated solution. What's a saturated solution? Saturated solution is a solution that you had dissolved as many of the solid as you can possibly dissolve, and there's no way you can dissolve anymore. That's a saturated solution. You can do that at home right now. Go get a glass of water and then get salt, and then keep adding salt to water. Keep adding until you can't add the salt anymore. If you add the salt, it doesn't dissolve, stays in the solution, then you have made it a saturated solution. You don't actually have to go do that. Just, I'm just saying that you could. All right. So we're going to make a saturated solution. How are we going to do that? The way we're going to do that, the same way I just told you how to do to make a salty saturated solution. We are going to have water in here, okay? And you are going to keep adding sodium borate. We're going to keep adding sodium borate. If it dissolves, we're going to keep adding. We're going to keep adding. We're going to keep adding until there are solids here and you cannot dissolve anymore. Then you have made a saturated solution, okay? So, one more time. Again, we're going to have our water, and you're going to keep adding your sodium borate. You're going to keep adding, you're going to keep adding, you're going to keep adding until there is solid in the solution. That means you have added as much sodium borate as you can possibly add, and you can't add any more. And then what that means is, that means that you have a saturated solution. So again, you're going to keep adding until you are going to have excess borate, sodium borate in here. So far, so good? Okay. All right. Now, when we do that, then we are going to figure out how much borate has dissolved. Okay? We're going to figure out how much borate has dissolved. And then once we figure out how much borate has dissolved, we can also use a mole ratio to figure out how much sodium was dissolved. And then we're going to get to that in a second. Now, we are going to analyze this solution, right? We have a saturated solution. We are going to analyze this solution. Here's what I need you to understand, is that in order to analyze the entire solution, we don't need to take this whole thing. You don't need this entire solution to analyze this. What you can do, you can take a sample of this. So what you can do, you can just take a sample of this and analyze it. And what we call that, we call it aliquot. So that's a kind of fancy word for today. So we're going to take an aliquot, which means we're just going to take a sample of this solution to analyze it. I think what we're going to take 10 ml of this solution. Okay, again, we don't need to take the entire solution to analyze this. We can take a sample and we call it an aliquot. So we're going to take a 10 ml aliquot of this solution and we are going to analyze it. Now, why is it okay to only take a 10 ml and then analyze it? It's okay because remember, if you take 10 ml of it, it's going to have the same concentration as the entire solution here. because when things dissolve in water, they're going to dissolve uniformly. So if we just take a sample of this, it's still going to have the same concentration as the entire solution. One example I used to use in my Chem 38 all the time is like having 2% milk. If you have 2% milk at home, it doesn't matter if you take 1 glass of that, 2 glasses of that, you drink the whole thing. Doesn't matter how much. If you take a sample of a 2% milk, it will always be a 2% milk. This is exactly the same idea. Doesn't matter how much of this I take, this is going to have the same concentration of this. It's still going to have the same concentration. So far, so good? Okay. Remember I said that delta G and equilibrium constant are related. And we talked about this at the beginning of this lecture, that delta G and equilibrium constant are related. It's great. Now, the equilibrium constant here is KSP, right? The equilibrium constant is KSP, solubility product, because we have solid and the solid is going to dissolve and it's going to go into AQ, and our equilibrium constant is KSP, solubility product, because we're looking at how much of the solid is going to dissolve in water. Now, also remember that when you have delta G has 2 parts to it. It has delta H and it has delta S. Don't forget that. And we can also do a standard condition. So delta G has 2 parts. It has delta H and delta S. Now, I talked about it at the beginning of this lecture. Then again, these are related. Delta G and K equilibrium are related because energy is a driving force for a reaction. So the tendency to reach equilibrium is driven by delta G. Now, if you remember from lecture, there was an equation that was relating these two together. And that equation was RT ln of K equilibrium is equal delta G. That was the equation that was relating these together. Now, I want to do something to this. So it was RT times ln of K equilibrium equals delta G. What I'm going to do, I'm going to change this just a little bit. I'm going to say RT ln of KSP, because again, my equilibrium constant is KSP, is a solubility product, because I'm looking at how much of the borate will dissolve in water, equal, instead of delta G, I'm going to put delta H minus T delta S. And that's okay, because delta G equals delta H minus T delta S. So I took this. I knew my K equilibrium specifically is KSP. It's like KA, KB, KW. This is KSP. And then delta H minus T delta S, because delta G equals that. Then what I'm going to do, I'm going to move this around a little bit. I'm going to move this around a little bit. And I'm going to solve for ln of KSP. If I do that, I'm going to move things around. I'm going to rearrange it. Then what I end up getting is minus delta H over R times 1 over T plus delta S over R. So I took this equation and I rearrange it to solve for ln of KSP. Now, I like this form because you have seen this form before. When you look at this, what can you tell me about this form? Think about kinetics. We had this in kinetics. When you look at this, this is a linear equation, isn't it? It's a linear relationship. Y is equal mx plus b. So, let's take a step back. I want to make sure you understand this. So here's an equation that relates delta G and K equilibrium. I took this equation. Instead of K equilibrium, I used that KSP here, is the equilibrium of solubility product. Delta G equals delta H minus delta T. minus T delta S, nothing new. Then I rearrange this into this format. And the reason I love this format, because now this is a linear equation. There's a linear relationship here. Y equals mx plus b. Now, does this look familiar? Yeah, Arrhenius plot. Yeah, that's probably what you're thinking about. Arrhenius plot. It does look familiar. Now what am I going to do? I'm actually going to graph this. Let's graph this. So, I want you to do this before you watch my graph. How would you graph this? You know this already. To graph this, I'm going to have 1 over T on my x-axis. On my y-axis, I'm going to have ln of K equilibrium or KSP in this case, okay? Because again, this is my x, that's my x-axis, this is my y-axis. So I'm going to graph these together. Now, what's gonna happen, and you're gonna have data points, right? We're gonna have data points, and this is going to be a linear relationship. This is going to be a linear relationship. So far, so good? Okay. Now, one thing I want you to pay attention to, and this is what's a little bit different than the kinetics, this is the slope, right? You have the slope. The slope is this is my slope, right? The slope can be plus or it can be minus. You can have upward or downward slope. So the slope can be plus or it can be minus. Yeah? Okay. Again, we had a linear format, and then all we did, we plugged it in. That's all that we did. And then remember that the slope and the b, they could be plus or they could be minus. All right. Very nice job so far. Before we move on, I want to point out one more thing that is very key. And that is, remember I just said that the slope and the b could be positive or could be negative. And what I want you to be thinking about is that when I talk about the m and the b could be positive or could be negative, you can kind of think about what you would expect. Because again, the m is delta H, the b is delta S. What do you expect when you have the solution of sodium borate in water? Do you expect the delta H and delta S to be positive, or do you expect them to be negative? So think about that. You can kind of predict that before we get the answer. Now that we've talked about the concept, I want to go back to the experiment. So we said at the beginning, we're going to do a titration. And what a titration is going to do, titration is going to give us the K equilibrium, if you remember. So now let's go. And again, the main thing is what a titration is going to give us is going to give us the K equilibrium, which you know in this case is KSP. So let's go over how is the titration are going to give me the K equilibrium, which is in this case is KSP. I know you know titration, but I want to quickly go over the setup again. So I'm going to titrate this solution with hydrochloric acid. And down here, I have my 10 ml aliquot. Okay? And also, I need an indicator for the titration. Now, I know you know this, but I want to say it one more time just to make sure we're on the same page. You don't forget about the big picture. Remember, we made a saturated solution, right? I'm going to come back here. We made a saturated solution. We added as much as sodium borax that we could. We took an aliquot, we took a sample of this solution. Now, what we're going to figure out, the whole point of this, we wanted to figure out how much borate actually dissolved. So we want to figure out how much borate was dissolving in this solution. So don't forget of the big picture. So I'm going to come back here. So when I do a titration, I'm going to have an aliquot, the 10 ml sample of my saturated solution, and I'm going to titrate it what am I trying to figure out? I'm going to try to figure out the concentration of borate. I need you to remember that what are we trying to get? What's the goal? I'm actually going to write this down. What is the goal? The goal is to figure out the concentration of borate. Borate. The goal is the concentration of borate. That's what we need. We need the concentration of borate. All right, so let's come back here now. So I have my aliquot here. I have my hydrochloric acid here. And to be able to do a titration, I need to know the exact concentration of hydrochloric acid. So you may have to do a standardization. You may have to standardize it because you need to know the exact concentration of hydrochloric acid. Okay, then we're going to start titrating. We're going to titrate, we're going to titrate, we're going to titrate. You're going to keep adding hydrochloric acid until you reach the end point. And what does it mean? What does the end point mean? So you are going to keep adding hydrochloric acid until you reach the end point. What the end point means, that means all borate have been consumed by hydrochloric acid. So that means all borate have been consumed by hydrochloric acid. And when that happens, what am I going to have? I'm going to have a color change. Okay, so I have my hydrochloric acid here. I know the exact concentration. I have my sample here. I want to keep adding hydrochloric acid. I want to keep adding until I reach the end point where there's going to be a color change. And when all the borate have been consumed by hydrochloric acid, that's where I'm going to reach the end point, and that's where I'm going to have a color change. So by doing this, what you are going to do, you are going to figure out the concentration of borate. Once you figure out the concentration of borate, what can you do after that? You can figure out the KSP. So once you figure out the concentration of borate, you can figure out the KSP. Now we're going to do this experiment at different temperature. So then what we are going to be able to do, we're going to be able to get the KSP at different temperature. So if I have KSP at different temperature, what I could do, I could plot ln of KSP over 1 over T. That's pretty cool. So if again, I'm going to do this experiment at different temperature, so we're going to get KSP at different temperature. Now if I have those information, I can plot ln of KSP over 1 over T. If I do that, what kind of information can I get out of it? I can get delta H and delta S based on that graph. So what that graph is going to give me, that graph is going to give me delta H and delta S. Now, if you have delta H and delta S, what could you figure out from there? You can definitely plug it into the formula and you can get the delta G. That's pretty cool. Again, we use the relationship between K equilibrium and delta G to be able to get the variables that we want. All right. Nice job. Thanks for hanging in there with me. I will talk to you guys soon.